Hello, this is Miss Moore, and today during chemistry we're going to discuss Dalton's law. Today's essential question: how is Dalton's law used with the other gas laws? Dalton's law deals with the variable pressure. So let's spend a few minutes talking about pressure and the factors that affect pressure. The pressure of a gas is the force at which the gas molecules collide with the container. Gas pressure depends on the number of particles in a given volume and on average kinetic energy. So the number of gas particles in a container can change or will change gas pressure. So a larger number of gas particles will collide with the walls of the container more often, leading to greater pressure. While a smaller number of gas particles will collide with the walls of the container less often, leading to a smaller pressure. Volume or size of the container can also change the amount of pressure. A gas in a small volume container will hit the walls of the container more often, resulting in greater pressure. The same amount of gas in a larger volume container will hit the walls of the container less often, resulting in a lesser pressure. A change in temperature will also change the amount of pressure, keeping in mind that temperature is directly related to kinetic energy, meaning that as the temperature increases, kinetic energy and molecule movement will increase, and as temperature decreases, kinetic energy and molecule movement will decrease. Okay, so an increase in temperature will lead to an increase in pressure because the molecules will be moving more, resulting in more collisions with the side of the container. Conversely, a decrease in temperature will lead to a decrease in pressure because the gas molecules will be moving less, and there should be another S there, resulting in less collisions with the side of the container. All right, on to Dalton's law of partial pressures. Dalton's law deals with pressure of a mixture of gases. For example, air. Air is made up of lots of different gases. So Dalton found that in a mixture of gases, each gas exerts a pressure as if it were alone in the container. All the gases in a mixture are at the same temperature and have the same volume. So the pressure of each gas is proportional to the number of molecules inside the container. Dalton's law of partial pressure says the total pressure of a gas in a mixture is equal to the sum of the partial pressures of the individual gases. Okay? And Dalton's law is P total, P standing for pressure. So P total equals the pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3, and so forth for however many gases are in the mixture. So again, Dalton's law says that the total pressure of a gas in a container is equal to the pressure of the sum of the pressure of each individual gases in that container. All right, let's try a quick practice problem involving Dalton's law of partial pressures. So our practice: air contains oxygen, nitrogen, carbon dioxide, and trace elements of other gases. What is the partial pressure of oxygen at 101.30 kPa of total pressure if the partial pressures of nitrogen is 79.10 kPa, of carbon dioxide is 0.040 kPa, and the other trace gases is 0.94 kPa? Okay. So first let's recall Dalton's law of partial pressure states that total pressure equals the partial pressure of each gas. So in this case, we have the pressure of oxygen plus the pressure of nitrogen plus the pressure of carbon dioxide plus the pressure of, trace gases. And from here, we just plug things in. So let's see, what do we know so far? We know that we have a total pressure of 101.30 kPa. We are looking for the pressure of oxygen, so that'll be our X. The pressure of nitrogen is 79.10 kPa. The pressure of carbon dioxide is 0.040 kPa. And finally, the pressure of the other gases is, or trace gases, is 0.94 kPa. All right, so now to solve for X, let's start by doing some basic math here. Let's add together the partial pressures of all the gases except for oxygen, which gives us a partial pressure of 80.08 kPa. Now, to solve for X, we'll just subtract 80.08 kPa from both sides. Giving us a partial pressure of oxygen of 21.22 kPa. And let's check our sig figs really quickly. Let's see, we have 5 sig figs there, and 4, and 3, and 2. So we're going to have 2 sig figs. So our final answer is 21 kPa. So the partial pressure of oxygen in air is 21 kPa. Okay, let's try one more problem together, but this time we'll be using Dalton's law in conjunction with other gas laws. Now, these types of problems take a lot of thinking. You really need to look at what kind of things are given, what is being asked, and then step back and think about what gas law or laws can you use to answer the question. All right, so we have a 12-liter container has 2.5 mole of nitrogen gas and 5.5 mole of oxygen gas at 345 K. What is the total pressure inside the container? All right, so let's start with the question. We're looking for total pressure. So if we're looking for total pressure, somewhere in here there must be partial pressures. However, they don't give us any more partial, they don't give us any other pressures. What do they give us? They give us volume, they give us moles of 2 different gases, of nitrogen and of oxygen, and they give us temperature. So again, the variables we have are volume, moles, temperature, and pressure. Sounds to me like the ideal gas law. P for pressure, V for volume, equals the number of moles times the constant R times temperature. So I think what we should do is solve for pressure of nitrogen and solve again for pressure of oxygen. Then we can add those 2 pressures together to come up with a total pressure. All right, so let's list our variables. We've got P, V, N, the constant R, and T. Let's start by solving for nitrogen gas. All right, so pressure is what we're looking for. We don't know that. We know our volume is 12 liters. The number of moles of nitrogen gas is 2.50. And the temperature is 345 K. All right. Because we don't know the pressure, and because it doesn't say what units the pressure needs to be in, we can just pick. I think I'm going to go ahead and pick the ATM. So we're going to have 0.0821 liters ATM over mole K. Okay, let's plug this stuff in to ideal gas law and see what we get. So we have P times V equals N, the N for nitrogen, times R times T. All right, and first thing we can do is let's cross out any units that we can. We can get rid of mole and K. So now we have X times 12 liters equals 70.81125 liters ATM. And to solve for X, we'll divide both sides by 12 liters, allowing our liters to cancel out. And that gives us 5.9009 and so forth ATM. So let's go back and look at sig figs. We have 4 and 3 and 3. So our final answer, so the pressure, the parcel pressure for nitrogen gas will be 5.90 ATM. Okay, so now we need to use the ideal gas law again and solve for the pressure of the oxygen gas. So our volume is again 12 liters. We're still looking for pressure. This time we have 5.5 mole of oxygen gas. I still need to use the ATM unit, and our temperature is still 345. Okay. All right, let's solve again, this time for oxygen. So we have P times V equals N times R times T. Okay, cross out units, our moles cross out, our K's cross out. So we now have X times 12 liters equals 155.78475 liters ATM. And to solve for X, we'll divide both sides by 12 liters, which crosses out our liter units. And that gives us a pressure of 12.98206 something something ATM. And let's go back and look at sig figs. We have 4 and 3 and 3, so 3 sig figs. So the partial pressure of oxygen is 13.0 ATM. So now all we need is the total pressure, which is what the problem originally asked us for. So when we add those two partial pressures together, we come up with 18.9 ATM. All right, so that is one way to use Dalton's law in conjunction with other gas laws. And that's it for today. Have a good one.